Now in this slide, in this video, I will discuss the shortest path problem, the all pairs shortest path problem. And to illustrate this, I'm using a very small directed weighted graph. And the all pairs problem is to find the minimum cost path from any one vertex to any vertex. Now, if the vertex at the start and end are the same, then the path is trivial and has zero length. And we need to produce the answers in the form of an array, where, for example, we have B here, and 1 is the minimum distance from B to A. Minus 2 plus 1 plus 2 is, of course, 1. Now, this particular array is the back array. The cost array is n by n, but the back array is also n by n, because every element, every one of the n elements has n, actually n minus 1 back pointers. And for example, what is the shortest path from B to A? Well, I look at B to A, and this gives you a D. Now what that means is that D is to the next to the last element on that path. In order to finish the path from B to D, we have to be able to look at the path from B to D, and the last one is a C. And the path from B to C, we see the back pointer is B. So the next question is the path from B to B, and the answer is that's the trivial path B. Now, this particular fragment here, this is a recursive function which prints the path from X to Y. And let's take, for example, the path from C to A. Now, what happens is this, it's recursive, it has to basically go backwards. If we're printing the path from X to Y, then that path consists of only one vertex itself, X, which we'll call, we could say Y. But if it's not that, then we have to recursively print the path from X to back Y. Now, of course, this should be back XY, because the back function has two parameters. Namely, you want to get the last vertex before Y, but you have to know where you're starting from. Like the path to Y might have two different back pointers depending on where you came from. All right, now, but then after that we print Y, and then we return going back to the parent procedure that's called. Now, I will do a slight example of this. Suppose we're trying to find the path from C to A, and that path is C, D, A. How would we do that? We would call path CA. Now, since this is not equal, C is not equal to A, we don't do this. Instead, we call path from C to back CA, but back CA is D. If you look carefully at this, back CA is D. Now those are not equal, so I then call back C, and then what's back CD? Back CD is C. And so this will then call path CC. And when we call path C, we enter this branch, which prints out the value C. But then we have to peel back out of the recursion, and so when we finish the execution of back CD, it will print D. And then we have to finish the recursion, the call to path CA, which causes it to print A. And then it ends. So now you see we actually printed C, D, A in the correct order. we're going to learn two algorithms for the all-pair shortest path problem. The Floy-Warshall algorithm is relatively simple. It takes n cubed time, and it works for any directed weighted graph, providing there are no negative cycles. The Johnson's algorithm takes time. It's actually more complicated than Floy-Warshall, and its time is O(n) times m times log n, where m is the number of edges. Now, remember that n could be n squared. So if m is n squared, Johnson's algorithm takes longer than the Floy-Warshall algorithm. However, most graphs in real life are sparse. And so it's typical that Johnson's algorithm would take less time than the Floy-Warshall because m would typically be less than n over log n. But we'll do the simpler one first, which is the Floy-Warshall algorithm. Okay. All right, now we'll do the Floy-Warshall algorithm next. This one takes n cubed time, and there are basically no shortcuts. It takes only n squared space because it generates the two arrays, which I showed you earlier, the array cost and the back pointer array. So n squared space, n cubed time. Now the concept of Floy-Warshall is relatively simple. It's a relaxation method. Let us, for example, suppose that x, y, and z are vertices, because we're going to assume that our graph G is a set of vertices and a set of edges. So suppose I have x, y, and z are vertices. And let us suppose that we're in the middle of our calculation and we have computed a path from x to y, and we have computed a path from x to z. Now this path could have any number of edges, and this would have any number of edges, but we have also computed a path from x to z. Now in the outer loop, the main outer loop of the Floy-Warshall algorithm, at any given iteration of the main outer loop, we get paths between every pair of nodes. And that means that but then we can improve them. For example, if we have a graph here, let's say that this distance is 10 and this is 23, and this distance we've gotten is 40. And this is the cheapest path we have found from x to z so far. Now, when we look at these two paths, we can see that I could combine them to form a path from x to y, because I could simply follow this path concatenated with that path, and that would give me a cheaper path from x to z, which means that this one here would no longer be the best one. And that process is called relaxation. And that's the main, that is the main subroutine that is used in most of these shortest path problems. Okay. Now, we're given a graph G, and V is the set of vertices and E is edges. And the graph is really an ordered pair. It's a directed graph, and it's a weighted graph, meaning that for every edge E, a W of E is given. Now, there isn't necessarily an edge between every pair of vertices, so it is possible that WE does not exist, in which case we'll take it as a default value, which we call infinity. Now, of course, infinity is not a number, and there's no way you could store the word, the infinity in the computer. So you have to be somewhat clever to figure out some substitution for that, perhaps use an extremely large number, which is considered to be a kludge. And an alternative is to have a Boolean value which tells you that you have an actual real number, and that Boolean would be false if it's infinity. So our job is to compute the cost for each pair of vertices. The vertices are numbered from 1 to n. The edges are numbered from 1 to m, where m could be anywhere up to n squared. And we are to compute cost vi vj, which is the shortest path, or the weight of the shortest path from vi to vj, and back vi vj, which is only defined if I is not equal to j. And back vi vj is the second to the last vertex in the shortest path from vi to vj. Now, we then have to initialize the the program, and I could start over again with the new whiteboard here, but I'm going to show right here how to initialize. Initially, the cost from vi to vj is initialized at infinity for every pair. But if there is actually an edge, we're going to alter that. So first we make all of them infinity, including the ones that are going to be real numbers. And then, if there is an edge from vi to vj, we set the cost of the path from vi to vj equal to the weight of that edge. So the way we think of it is this. If we have vi here and vj there, and if there is an edge which has weight w, then that edge constitutes a path from vi to vj. It might not be the best possible path, because there could be some other sequence of edges that have a lower value. Now, in this initialization here, there won't be a path between any two vertices, even if eventually there is. Because, for example, if I have another vertex here, there could be an edge there, but there might not be an edge from vi to vk, which means eventually we'll find a path, but not during the initialization. All right, we're not done. We're going to set the cost to be the weight of the edge from vi to vj if the edge exists, and the back pointer vi vj is vi. Now, why is that true? Because if we take this as a single path, a singleton path, in other words, a single edge, then the back pointer points back to the beginning. And so that's how that works. Cut. Here is an example. This is sort of the overview of the main part of the code after we've initialized. We have the outer loop here. For j goes from 1 to n, and the inner loops are for I and k. Now, when we do the substance of the loop, we're going to do relax I, j, k. In this case, for example, I is 20 and k is 30, and we have constructed a new path from I to k, which makes use of j, vj. Now, there is a loop invariant here, which is important. And the loop invariant says that after we have finished the loop for a given j, that for any I and k, even if those I and k are larger than j, or smaller, the shortest path we have found so far between I and k may include vj, but it may not include any v with an index higher than j in the interior. So if you look at the path here, from I being 20 and k being 30, j being 10, then the path that I have found from vi to vk is allowed to use v10, but it's not allowed to use anything like v11, anything that's more than 10 in the interior. Not counted. The interior is everything except the two ends. Now here is the code and the loop invariant I've told you about. And we're going to do a relaxation ijk. But what that means is we try to form a new, better path by combining the best path from I to j and the best path from j to k to possibly give a better path from I to k. Maybe it won't give a better path. So if the cost of this path plus the cost of this path is less than the cost of whatever we have before from I to k, which of course could be that we don't have anything, it could be infinity, then we're going to reset the cost of path from I to k to be the cost, the sum of those two costs, because the new path is the concatenation. And then back pointers are reassigned carefully. We want the back pointer from vi to k to be the old back pointer of the path from vj to vk. And the reason is that, well, that was the next to the last vertex of this path, so it's the next to last vertex in the concatenation path. So this procedure we'll call relax, and I want to point out something important. I'm doing relax ijk, and I have to have a triple loop. It's n cubed in length. I loop through all j, all I, and all k, but j is the middle index, the middle number, and yet I put that as the outer loop. That's necessary. Actually, if you don't do that, you'll get results, but they might not be correct, and you won't realize it, or you might not realize it. And of course, if you use it incorrectly, you can achieve the same effect by iterating this whole thing log n times. But that's not necessary if you put the middle index first as the outer loop. The first and third indices could be in either order, it doesn't matter.